Great. Thank you for having me here. It's my second year now, so it's a great conference to be at. No, we're not going to talk about movies. We're going to talk about Spegel, which is a stateless cluster local OCI registry mirror. Obviously a mouthful, but will hopefully make a bit more sense. Quickly about me, why you should care about me or something like that. I currently live in Amsterdam. I'm Swedish. I'm not doing this presentation in Swedish. I'm the creator of Spegel. I'm also the co-founder of Kvik, which is the company name running kind of the development of Spegel right now. If you're out there interested in Spegel and want to be a design partner, reach out to me afterwards. I used to also be a core maintainer of Flux, which is maybe why you know me, and I write posts that sometimes blow up on Hacker News. Great. Now you know everything about me that's actually valuable to know. So, put yourself in this situation. You're up late at night, you're getting alerts, you have an outage in your Kubernetes cluster, nothing is scaling, nothing's actually working, nodes are going down, going up, but really there isn't an outage with your cloud provider, it's just that the registry that you're pulling your image from is just no longer available. You're kind of trying to find a solution to these types of problems. You're wishing, oh God, why didn't I really kind of go through the different strategies ahead of time? But you're in that situation. Out in the wild, we see a lot of these types of problems. We either see these problems not only from outages, but rate limiting. Docker Hub is a typical kind of scenario where Docker Hub will even rate limit you if you're an authenticated user, and also paying for Docker Hub, you end up with rate limits. You get outages. Well, the last one was Docker Hub. I don't want to shit only on Docker Hub. Everybody has outages. GitHub Container Registries has a lot of outages too. ACR, ECR, all these have outages because it's not only a centralized single solution, it's also dependent on so many other kind of platforms in the background that are actually serving these layers. Bandwidth is limited. And we also see things like image removals. So it's not only outages that cause these types of scenarios that really affect our scalability and uptime. So we built all these very complex, auto-scaling clusters that are able to serve thousands of servers and meet all our compute demands, right? We've spent a lot of time, a lot of money actually building these solutions, but we haven't really considered, okay, great. It doesn't really matter if I have 1,000 servers. Because in the end, if I don't have the image running my actual business workload, all this scale is just for nothing. And it seems like we've kind of overlooked this type of problem. Hopefully, you're not up at 1 a.m. trying to solve this problem as it's actually showing up. You're kind of planting a tree or hedging your bets, really. So typically what we see is people running some sort of private registry. They're either running a stateful registry that you're copying all your images from public registries and storing them kind of close to wherever you are, or you're running some sort of pull-through cache that you're hitting, and as if the image isn't there, it's pulling it from the upstream registry, putting it on disk, and then serving down to your clusters, right? That's kind of what we're doing. But as we say, the best time to plant a tree is 20 years ago or now, and sometimes you didn't plant that tree 20 years ago. So what I ended up going to a talk maybe 6-7 years ago. This was back in the time when Kubernetes was still using Docker. So that's why we're talking about Docker in this specific case. But I was listening to somebody talk who didn't plant this tree of trying to hedge his bets. And he was up late at night and Docker Hub was down. And at the same time, because they were serving American customers, they had a lot of scale that was needed. So basically, the existing solution couldn't meet the demand. They're trying to create new nodes, but they couldn't pull the images that actually were serving the business applications. And he was looking at this, and he was trying to figure out a solution. And what he came up with is kind of ingenious, very much like a mechanical Turk solution. So he was SSHing into a node that he knew had the image. He'd run Docker export, and then he would SCP that exported tar file onto another server that was newly scaled and didn't have the image. And then he'd run Docker import, right? And it worked. And he spent like the next like 4 hours basically just going, new node comes up, SCP the image over, Docker import, and just kept on shifting images. It's a mechanical Turk solution, but it actually solved the problem. Before we kind of go any further, I think it's good to talk about foundations. Foundations are kind of like critical when talking about these types of solutions. And like out of interest, because we're talking about a lot about OCI today, has anybody read any of the OCI specifications? So, ooh, some hands. This is like a record. It's like four hands were up, so. Great, so OCI basically is mostly a standard. There are like standard implementations, but it's mostly like a specification in form like markdown files that specify how things work when it comes to like both images that you build, distribute. The image spec defines basically how an image is composed, so not actually the build process of it, but in the end, like how you package an image. What's interesting with an OCI image in itself is it's actually multiple files. So you have basically a index file. These are all JSON, by the way. An index file basically references a manifest. Originally, when Docker was built, indexes didn't exist. It was only a manifest. The manifest references layers. Layers are actually just binary data in tar format and a config. And the config basically defines how to start the container. And the manifest basically just like connects this together. Indexes were introduced later, mostly to solve the multi-architecture problem. So an index references multiple manifests, basically one manifest per architecture and operating system. Just to quickly, maybe if we can do this quickly, show here. This is a great tool called oci.dag.dev. It allows you to basically explore images and their contents from any registry. So this is actually the Spegel image. It references here, this is the index, and it has like a reference now to a manifest. And you see here the architecture is AMD 64, OS is Linux, and it references by a digest. So the digest it references, this SHA-SUM, is actually the hash of this file. So that's how references in OCI formats work. Let's see if we can, slideshow, do I have to go all the way? No, it does not. Great. And the reason it does digest references is actually also important because what you end up with is just a Merkle tree. So the idea here is if you try to change the content down here in the config, it affects the SHA-SUM of the index. So there's like a self-verification that you can't modify any content down the tree. That's basically the image spec. The distribution spec defines how to distribute these images. So this is like registries. It turns out that in the distribution spec, it is allowed to implement only the read parts of the registry. So you can just build a registry that only supports pull. That's what we're focusing on today, mostly because the push part is a bit more complicated. But really, to build a registry, you only need 3 endpoints. You need to respond with a 200 on V2, and that's mostly just for the client to verify that it's talking to a registry. And then you have 1 endpoint to serve manifests. The reference here is either the digest of the manifest you want or a tag. And you have another endpoint to serve blobs, and blobs are only served with digests. They are separate endpoints for specific reasons, mostly because of like blobs are generally a lot larger than manifests, so you want to do like specific to like file handling there. And that's really all you need to do to implement a OCI compliant registry. Simple. The last thing that we want to talk about is just quickly give some understanding of containerd and how it does image storage. So when containerd, which is what is kind of like the de facto way we run containers today, runs a container, it actually has to pull down the image. And what it does is it actually stores this image on disk. So it's downloading all the layers, sometimes in parallel, and just puts it on disk. And then after it's done that, it does like decompression and actually like unpacks this into like a file environment that is like possible to run the container. Right, so this is like kind of like the foundations, and after this, we've hopefully learned something new together. So back to this 1 a.m. situation. I kind of left that in the back of my head for 7 years. Thought a lot about well, that was kind of like an interesting way of solving these types of problems. I spent a lot of time working on building Kubernetes clusters for different companies around in the Nordics. But time and time again, we'd kind of hit these types of problems, right? And I think everybody here who builds anything, depending on either public or private registries, have this type of problem. It's it's mostly availability, speed, and cost, right? And you can kind of get two, right? You can either be fast and high available, but it's going to cost you a lot of money, or you can kind of be highly available and cost efficient, but you're going to be paying on speed. But it feels like we constantly have these trade-offs and these challenges that we're kind of dealing with, and we're building more and more complex solutions to solve them. But even looking now, what happened, what was it, a week ago, 2 weeks ago when Docker Hub went down, the amount of people talking about not planting that tree, it's still there. We've moved from running Docker in our Kubernetes clusters to running containerd instead. And we've progressed in all these types of different solutions when it comes to scaling and running Kubernetes and all these different types of SaaS solutions. But we still haven't solved the image distribution problem. We keep on we're focusing on different things. And about 3 years ago, I ended up working a lot with a specific customer, and we had a lot of issues with GitHub container registries being down. And I was thinking to myself, well, there has to be a different solution. So maybe some background: those people don't know what the Mechanical Turk actually is and what it's based off of. There is obviously an Amazon service called mturk. Mechanical Turk is an illusion kind of thing where back in the day somebody invented a machine that could play chess, but in reality it was just somebody inside of the box playing chess, and it looked like this amazing kind of solution. But that was kind of the way that the original SCPing solution was solved. It was somebody sitting in the box, SCPing images back and forth in between different nodes. And I was like, well, we've invented chess-playing computers now, so we should be able to invent automating SCPing images to different nodes. Can't be that hard. And that's when I really started looking at different types of solutions and what we can build and what we can really offer here. And for me, and obviously I don't think Spegel is that original in itself. It takes a lot of components from a lot of other projects that try to do kind of the similar things, but it has a slightly different influence. Spegel is a different way of looking at things. It's instead of focusing on solving the highly available centralized registry, we shift things downwards, and we enable Kubernetes nodes to basically pull images from each other, right? So this is basically automating the SCP solution. And we can do this because we have our understanding of the OCI specification. We understand the distribution specification. And it really hits a lot of these types of different problems because we are no longer really dependent on these types of upstream registries anymore. It has some interesting impacts. One of them is that image pull performance increases by about 80%. I was mostly surprised, and I've seen numbers that are better than this, and I was very surprised when I first saw these numbers. But it kind of makes sense, because what really Spegel does is it enables Kubernetes nodes to pull from each other. And when we build Kubernetes clusters, we generally put them in private networks, and we try to put the nodes as close to each other as possible because applications need to talk across nodes. So if we just throw out the whole communicating with the internet or outside of our own private network, we kind of get crazy speeds when it comes to distributing images. Just to give some kind of understanding of the architecture. As somebody who has spent a lot of time over the last 3 years working on Spegel, this makes a lot of sense to me. So if it doesn't to you, please tell me that I'm making things a bit too complicated. But Spegel in itself, in its essence, is really 3 things. It's a pull registry. So what it does is it basically runs a read-only registry on every node as a daemon set. And then it uses, as we talked about, when containerd runs a container, it puts the images on disk. So the registry serves the images that containerd has already pulled and stored on disk. And then the third component, and I think this is like the one that I enjoyed the most when I built Spegel, is the lookup part. So what happens is the kubelet down here talks to, obviously, the Kubernetes API. It notices that it has to start a pod, so it tells containerd through the CRI API that, like, hey, you have to start a container. Containerd goes, well, I don't have it on disk, so I have to pull, I haven't cached this image yet, so I have to pull it from somewhere. Containerd will read the mirror configuration, and what basically Spegel does is it configures the mirror configuration to basically point to localhost and pull from the local registry that's running on the host itself. So Spegel gets this pull, the actual request, and then it does a lookup. And it forwards the request to another node within the cluster that actually has the image cached by containerd, and then it serves it. So it's just basically like the local instance just proxies traffic. I spent a lot of time working on this problem initially, and I feel very embarrassed with the different solutions I built. I implemented different solutions with like Postgres and Redis and all these types of different things, because it's like, in its essence, the problem is, well, you can run all your local registries, but they're only valuable if they can find other nodes in your cluster that already has this image. And how do you do this at scale? And in my initial development, I wasn't really thinking about scale. I was thinking about like maybe 50 to 100 nodes. And none of these things really worked. And also, I didn't really want to introduce more state, because that was also like the operational burden. I was trying to say, like, look, all these centralized registries aren't able to scale, so I can't just go, my solution also is a centralized registry inside of your cluster. I eventually realized that I was trying to solve a solved problem. And basically what it is, it's a bunch of computers with files that they're trying to share with each other and tell each other which files they have. It's basically BitTorrent. So once you realize that, you go, oh, I wasted like a month trying to like build different implementations. Let's just go on Wikipedia, look up BitTorrent, and go, what does BitTorrent use to discover this? Because BitTorrent scales like across the whole internet with millions of computers and is able to do this file discovery. It turns out that BitTorrent uses a distributed hash table, specifically an implementation called Kademlia. Kademlia is really cool because it the way that lookups work scales really well in like very large environments. So what happens is basically Spegel has like its own distributed hash table in between all the different peers, and is able to, within like milliseconds, look up basically the individual digests. And so what happens is Spegel will look at all the files it has on disk and just advertise it out to all the other peers that it knows about. And then the lookup in reverse basically walks the distributed hash table to find another peer and then just forwards the request. And this goes on all like sub 4 milliseconds basically. So that's the additional latency that you're adding to serving these mirrors. Spegel is growing. These are the official adopters. If you're using Spegel out there, please add yourself to the adopters list. It's always fun seeing different companies and organizations using Spegel. I run a community meeting. Somehow I end up always doing conferences on Tuesdays, so it always collides with the community meetings. I'll see if I can make that one. But yeah, we also have a Slack channel in the Kubernetes Slack, so come say hi, share your experiences, fun stuff like that. So let's talk a bit about the future. So initially, when I built Spegel, I did it to solve a specific customer case. So we were running 50 node Kubernetes clusters, but for like the e-commerce kind of like situations. And we were seeing a lot of issues with GitHub container registries going down. They weren't happy because they were actually losing customers. But they were also in like some sort of like budget spend limit where they weren't willing to pay to run like registries and have somebody actually like operate them and have SLAs on them. So I built it for like that type of scale. And initially when I made Spegel public, I got like the two typical kind of use cases. So the main one was like people having the same problems as me, running smaller clusters, trying to solve like these types of like budget constrained problems. The nice thing with Spegel is it uses around like 20 megabytes of RAM on each node to do all the lookups and stuff. So like it's very minimal in that sense. And a lot of home labbers, people running Kubernetes clusters at home, getting Docker Hub rate limits, and they didn't want to either pay for Docker Hub or they were still getting rate limited through like when they were like repulling images all the time because they were doing this bunch of stuff. And that's kind of what I got initially. And then more and more people started using Spegel. And one of the things that I've seen a lot of recently is AI distributions. Hopefully, like now I've talked about AI, so everybody's really happy. No, but it's like a big problem with once you start running AI models in Kubernetes is that the models themselves are very large, which makes the images very large. And we're talking like 50 gigabytes to like nearly a terabyte in size. So these are very large images that we're trying to distribute in systems that really weren't built to, or when the systems when they were originally architected didn't really consider these types of use cases, right? So these are like, I didn't really think about this when I built it, but there are a lot of happy accidents that have happened with Spegel. The people I've talked to that run Spegel run it on like 1,000 plus nodes. Is kind of like the bigger clusters. I think like 2,000 is like the most I've heard somebody run, distributing like 100 plus gig images. So this is like a completely different scale than I had ever considered when I originally built Spegel, but it scales pretty well. One really fun kind of like a happy accident that Spegel solved is node churn. So I'm guessing some people here are using like Carpenter and different types of like as like an autoscaler, and some people set TTLs on their nodes, so they want like a node to only live for example, a day, or they're scaling up and down a lot. What Spegel did that I really never considered was that these types of scenarios are really interesting. You have, especially if you have proper pod disruption budgets set up, if you have a node running and you want to evict it, but the pods need to keep on running or need to move to another node, you end up in this really funny scenario. So if you have proper pod disruption budgets, your node will get cordoned and drained, so new pods won't get scheduled, and it will try to push out the pods to a new node. And this new node might also be a new EC2 instance that it's starting up. So what happens is basically the pods that are running on the evicted node won't disappear until the new pods start. So you get this new VM that starts, new pods start there, and what happens is they basically pull the images from the existing node. And this is like a typical scenario that you end up with like, especially if you're investing a lot in like running spot instances. And I've talked to people where you end up in a scenario where you're investing heavily and you're saving a lot of money on running spot instances, but you end up actually paying more money to pull the images because now you're pulling images a lot more often, right? So this is like one of those things that I like, the first time I saw this happening in action, I was like looking at it, I was like, this makes no sense. And then eventually you kind of go like, yeah, it makes a lot of sense. And the scalability of it is actually like really cool because you see like new nodes come up about like 50% faster than they used to, just because it's able to shift images in between different servers. Another one that's seen, another AI slide, great, is kserve. So a typical issue when you're running like kserve and like trying to run LLMs in Kubernetes is that you're, by default, what happens when you run kserve and you're pulling, for example, LLMs from like Hugging Face, is that VLLM will start and it will download the model and put it into ephemeral disk on your pod. and this LLM might be pretty large. So like, sure, your VLLM starts, but it's not ready until the actual model is pulled. And especially if you're doing this at scale, you end up with like a lot of like startup latency issues. So there are some happy accidents that have happened here. So one of them is that OCI artifacts have been introduced into Kubernetes. I don't know if it's GA or not. I think it is, maybe. Spegel does support OCI artifacts. So what OCI artifacts or volumes basically are is basically it allows you to take a OCI image, and instead of using it as a way of running a container, you take the contents of that image and mount it onto another container. So what you're able to do then is you're able to take the runtime of your LLM and the model that you're using and separate them into two separate images. But because they're all cached on disk, you can use Spegel to basically distribute this. So as you're scaling and you're trying to pull your models, you can basically have one node pull the LLM once, these 50 gigabytes, and then they exist in your cluster, and then as you're trying to like scale up and run more replicas of your machine learning model, you're able to basically pull this a lot faster, up to around 80% faster. So yeah, so these are like kind of use cases that I've been seeing, that I've been working on, that I really didn't really consider initially when I was developing. One of the challenges really is with Spegel that I've been working on lately is first pull. So the challenge is really like you want to pull an image into a cluster, and you end up with this scenario of like, especially if you're running a lot of pods at scale, you're in a scenario where you're using a new image, you start a bunch of pods. They all come running. And because the image isn't cached in the cluster, you're kind of like, all the nodes end up pulling the image at the same time from the upstream registry. And that's kind of what you don't want. So what you actually want is a scenario where you're able to prefetch images and basically pull an image once. And it's kind of like you don't want to do it too late or too early. You want to do it like at that perfect date. And that's kind of like what I'm looking into the future now is like seeing is like what are the other things that we're doing? Like Spegel works really well in scenarios where images already exist in the cluster. But problems like first pull is like one of those things that like Spegel doesn't solve today, because you either end up in a situation where you have all the pods starting at once with a bunch of nodes trying to pull the images down from the upstream registry, or you have the other solution, which is you have one node pull the image first, but now when the 49 other nodes come up, they all hit that single node, and you saturate the bandwidth. So I've been thinking a lot lately about like what other solutions exist out there. And building Spegel, like I've talked to a lot of companies in like larger scales than I've ever worked at. I haven't worked at companies doing like cool shit running thousands of nodes. But like they've come with like very interesting problems, really. Problems I really never even considered Spegel would have. And it's gotten me thinking, like, we try to solve a lot of these fundamental issues with tools that we already have. And I'm not saying projects like Harbor or Zot are bad. I think they're great. I think they're awesome. I just think that we're trying to take a hammer and apply it to every type of, like, see everything as a nail. So we're trying to, like, take this mentality of centralized stateful registries and apply it to a mindset of ephemeral containers and clusters. We keep talking about, oh, cattle, not pets. But we don't talk that way about our registries, right? And even when we run like multi-regional distributions, we even then say, oh, great, we need a image distribution strategy where we run multiple stateful registries and we try to like shift images from one centralized registry to the next. And before we think about, and we like take a step back and we look, we realize we're running 5 different registries. Even worse if we're running multi-cloud, because then we're doing we have like an ECR registry here and an ACR registry there, and then a harbor registry in our data center. And there has to be a different way. There has to be some other solution that gives the same type of value, but solves it in a lot cheaper way. And that's like looking at Spegel. The one reason a lot of people come and start using it is because, well, it's stateless and operationally it has very low cost. So the idea is basically, can we apply the same types of ideas of like low operational cost and statelessness to solve regional image distribution at scale? And this is kind of like what I'm working on right now is basically implementing a regionally aware, topology aware prefetching solution that is able to basically pre-distribute images to clusters, and instead of having a registry for each cluster, we instead can treat the clusters as registries. And I think that's like when we start realizing that, well, while our nodes might be ephemeral, if we replicate images enough, we can deal with VM outages, and we can basically scrap these regional registries completely and basically go, well, every cluster is a registry now. Every node is a part of a registry, and clusters can actually communicate with each other and share images. Because what we really want is we want to move the images from these like far away places and move them as close as possible to where we actually run our workloads. And there isn't anything closer than using the literal node you're running your workload on as the registry. Doing pretty good on time. So that's kind of like my only company pitch slide. That's why I'm working on Qwik. Qwik is trying to solve these types of problems, especially in like large AM models, edge clusters, and multi-region deployments. So I'm trying to like build a larger solution on top of Spegel. Mostly like trying to like solve a lot of these like enterprise problems that you generally don't see if you're running like smaller clusters. And if you're interested in talking about that, or just Spegel open source or stuff like that, please reach out. I have stickers if anybody wants stickers, so just come talk to me afterwards also. Great, thank you so much. Any questions? Maybe, no. We have one down there. Do we need a microphone? Maybe not.
Please settle down so we can.
How do you handle images that change? Like if you have a Java 21 image or whatever, how do you update the cache?
Oh, you're doing reusable, like reusable tags? Don't use reusable. No, okay. I think in a perfect world, we wouldn't reuse tags, especially once you start like looking into like how that works. You go like, ugh. But like the reality, and like the same thing is with people using latest tags. In the documentation, there is like a guide. There's a project that Google created called Kate's Digester. It runs a mutating webhook that if you basically use a tag reference, it will actually resolve the digest and then add the digest to the image reference. And that way, you always get the latest one from the upstream. In the larger tracker that I'm building as part of the enterprise solution, I've gone a step further. I'm going to actually build a Spegel-aware one. So the problem with Kate's Digester is if the upstream registry is down, you're not able to resolve the latest digest. So what basically I've built is a version that will first check the upstream registry, but then also check the Spegel cluster to resolve the latest digest instead. Yeah, so that's kind of how you solve it. Other questions? Yes, one there.
So technology-wise, when the nodes talk to each other, they're going to get the manifest and then say like, oh, actually I have 3 or 4 layers already here. So they download the layers on the other nodes, not the image completely, or? So
what happens, okay, so we can like actually walk through this pretty quickly and easily. So what Containerd does when it pulls an image, it gets the reference is like the registry, the namespace, and then like the tag or the digest. it will go and fetch the first manifest. So like the index or the manifest, it doesn't really matter. And then it will, if it's an index, it will go look in the manifest or the index file to go like, I want this architecture. So it looks at like, I'm running on a AMD 64 Linux machine, so I want the manifest for that architecture. And then it gets that. And then it looks in that and goes, these are the layers that I need to get. And so what all these parts are stored on disk. When you like, that's the whole image, that all these individual files, right? But getting each layer and each manifest is a individual HTTP request. So it basically gets the index, gets the manifest, makes a request, and then once it has the layers, containerd, there's an option you can enable, so it will actually start downloading the layers in parallel because it can get all of them. But yeah, so that's kind of how it does it.
Follow-up question. Saying you're using like P2P, so mean I can download, let's say, especially say parallel, I can download from different nodes at the same time to even get more speed.
So these are the kinds of problems that I've like working on right now. There is a I've made some different types of solutions or like POCs to like see what the performance increases are. Containerd actually has a feature now that you can enable in like 2.2, where you can add concurrency. So if a layer is over like 500 megabytes, it will actually start like 4 different Go routines. Hopefully they watched Sarah's talk before to like figure out that they don't end up in deadlock situations. And they basically, because the OCI spec allows you to do range requests, it fetches like ranges of the layer in parallel. The funny thing is, this was implemented by somebody who works at Hugging Face, and they're apparently downloading this from like ECR, which is technically just S3, if you look at like how ECR is actually implemented. And my assumption is, for them, it's only faster because S3 throttles you per request. And if you're running multiple parallel requests, you're actually getting 5 times the bandwidth, right? But that in combination with Spegel has like a lot of interesting like impact, because as you say, if containerd is doing 5 requests at the same time for parts of the same content, what I've built in Spegel is, and I think it's not in the current release, it's coming in the next release. I've implemented a new round robin feature, so it actually tries to spread out these requests to different nodes. And that actually increases the speed even more. Yeah.
Nice.
Yes.
So you mentioned AI models, right?
Yeah.
Primary use case, because they're absolutely fucking massive.
Yeah.
A lot of these AI clusters, they come with these really high performance fabrics. Have you thought about RDMA or DPDK as a data plane?
Yeah, that's a very great leading question. It's obviously like one of those things, like InfiniBand is like what kind of we were talking about also in this scenario. You can run like IP over InfiniBand. I'm not smart enough, Matt, you're probably smart enough to like tell us all about how to do this, but it's like, once you like, what's like really interesting is like the end users who are large running very large EC2 instances. And this is like the cool thing is in AWS, they tend to scale the bandwidth and the disk speed you get based on how large your EC2 instance is. So if you have a very large EC2 instance, it gives you a lot of bandwidth, right? So the larger the size of the VMs you have, the faster the distribution it actually is. But yeah, like eventually you're just going to be limited by how fast you can move bits between 2 machines in the same data center, basically.
Just one question.
Yeah.
Isn't what you're describing basically a distributed user mode file system?
Yeah, like there are things like what is it, Seaweed FS and these types of things. To a certain degree, it is, and there have been attempts to implement like distributed file systems, and I've talked to people who've done this. The challenge is really like you can do this. You can. I know that there are people who've like basically done like on like a kernel level or like a Linux level remote file system mounts on like a folder and then point a container D there and then just allowed everybody to like pull. The challenge is really partially there are some limitations of it that it's a bit too troubling to go through, but the other problem is the. So the challenge is really like from a usability aspect. So like the most Kubernetes clusters do not give you that type of access. It also requires you then to do these types of modifications to your nodes.
Which is why I said user mode. Basically, you don't go into code. You basically say that this runs just another process in my project.
Yeah, sure, and I think there are solutions out there. I don't know how many open source projects actually implement it. That's kind of like it is another solution that you could do. It's one that I haven't chosen to do.
Sounds like a great